All right, Algebra 1 and 1B students. In this video, I'm going to quickly kind of touch on the statistics that we were to get to here at the end of the year that we didn't quite make it to. So just so that you can say, all right, I've seen it, I kind of understand what she's saying, I made the video, there is no assignment for this, and I don't go very deep into it. So just as long as you understand the basics, that's what's important. First of all, statistics is a way for us to measure data when we collect it for whatever we're collecting it for. So if you are looking for information about a group of people, you could find their ages or their shoe size or how many pets they have at home, right? It's collecting numbers and then kind of analyzing the numbers and figuring out what's kind of the middle, what's kind of the average of all the numbers, right? Where's the central tendency? Where's the middle of everything? And then how far away from the middle of those numbers are all the other numbers spread out? So that's kind of what statistics are and what we're going to be talking about. I'm going to use a worksheet for this very first section, and then I'm just going to teach you on my own the other parts. So it shouldn't be too tough. Hopefully you can follow along, okay? Statistics and parameters. A statistic is a measure that describes a characteristic of a sample. A parameter is a measure that describes a characteristic of a population. Statistics can change from sample to sample, while parameters do not. So you could have a group of 1,000 people and you want to know, I don't know, how old they are, right? So you could pick 50 people out of those 1,000 and ask them how old they are. And maybe the average of those 50 people is 25 years old. But if you asked another 50 people, their average might be 37 years old, right? It just kind of depends on which 50 people, which sample you're talking about out of the 1,000. So either way, the samples can change from the entire group. The average age of all 1,000 people might be 21, right? But when you take smaller samples, that's going to change. So a sample helps us kind of guesstimate what the bigger population amount will be, the statistics there, but it's not always super accurate. Identify the sample and the population for each situation, then describe the sample statistic and the population parameter. So here it says, at a local supermarket, a random sample of 50 shoppers is selected. The median amount spent at the supermarket is calculated for the sample. So the sample here is the 50 shoppers. The population would be all of the shoppers that come to the store, right? So we're just picking 50, but there's a whole lot more than that come to the store. The sample statistic is what we're looking for. So the median amount of time spent by shoppers in the sample. So maybe of those 50 people, a few of them only stay in the store for 10 minutes, a few of them stay in the store for over 2 hours. We don't know, right? So that's what we're kind of calculating. And we can figure out from those 50 people kind of what the middle number is. And that middle number may or may not reflect what the average is for all the shoppers. We don't know. The population parameter is the median amount spent on all shoppers at the supermarket. So our sample statistic is just the median amount from our sample. The population parameter is that same measure for the entire population, okay? B, every 20 minutes, at a furniture factory, a finished sofa is pulled from the assembly line and checked for defects. The percentage of sofas in the sample which are defective is then calculated. So our sample is just the sofas that are pulled to see if they're defective, right? The sofas checked for defects. The population would be all the sofas, every single one that's made, not just the one pulled for defects. Sample statistic would be the percentage of defective sofas. So maybe they pull 10 sofas to check them for defects, and maybe 2 of those sofas have, a ripped seam, or maybe a leg is kind of crooked or something. They're defective, maybe 2 of the 10, right? So that's our sample statistic, how many out of the sample. The population parameter would be how many out of all of the sofas. Out of that sample, 2 out of 10 would be 20%, right? But out of all the sofas made, maybe only 8% have defects, right? So that sample might vary slightly from the population. All right, so I have 2 exercises here for us to do the exact same thing. Number 1, weather. A meteorologist places 10 weather stations in a county to measure rainfall. The average annual rainfall is calculated for the sample. So our sample is just the number of weather stations, right? The 10 weather stations. So 10 weather stations. And we're talking about like the little rain gauge, you know, the thing outside that you can dump the water out of that measures how many inches of rain you got. So the sample is just the 10 that were put out. The population would be the entire county, right? Entire county. Everywhere. Just because we put 10 weather stations out doesn't really account for all the rain everywhere. It just accounts for those 10 weather stations. And in Florida, you know, it can rain differently in different areas. All right, and then the sample statistic, sample stat, would be the amount of rain, whether the amount of rainfall, the average, the mean annual rainfall. So the mean annual rainfall in those 10 weather stations. In 10, I'm just going to put WS, in those 10 weather stations. So the sample statistic is the average out of the rainfall in those 10 weather stations. The population parameter would be the same thing, but for the entire population. So the mean rainfall for the whole county. I know you can't see all that. In the entire county. Okay, and then number 2, botany. A scientist randomly selects 20 trees in a forest. The mean height of those 20 trees is then calculated. So our sample is the 20 trees, right? Randomly selects 20 out of the thousands of trees. 20 trees. The whole population would be all of the trees in the forest. So I'm going to put pop. All trees in forest. Okay, the statistic is the average height of those 20 trees selected. So sample stat is the average height of 20 trees. And so the population parameter would be the average height of all of the trees. Okay, so all we want you to understand here, don't get caught up in the verbiage or you know, the wording, don't confuse yourself. It's just, we can't walk door to door like the census, right? We can't walk door to door. We don't have time to walk door to door and ask every single person all the info we need. So maybe we just ask 10 people, right? And we use that data as kind of a sample or an average to represent all of the people, right? It's just a quick, like, shortcut. And it may be accurate and it may not. All right, so for the rest of statistics, and I'm paraphrasing and it gives you a little more detail in the lessons, we had to cover lessons 12-2 to 12-4, but I wanted to start off with a set of data. So let's say we're looking at a classroom. Let's say it's our classroom, and in that classroom, we wanna use the data, everyone's age, because why not, right? And we're in high school, so I'll just kind of give a range of ages. I'm gonna say that there's 10 students in the classroom plus the teacher. So let's say the teacher is 36 years old, because I'm 36. Now, my birthday was yesterday. All right, and then the students' ages are, let's say we have 10 students, so let's say we have one 13, a couple of them 14. These are our freshmen. This guy's a baby. And then we have, let's say 1, 2, 3 are 15. Maybe a couple 16. A 17-year-old, and then a senior who's still got to take algebra to graduate, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Perfect. All right, so you guys should already know mean, median, and mode. Mean is the average, right? So how do we find the mean of data? Well, we're gonna add up all of the data and then divide by the number of pieces of data that we have. One thing I want you to notice here that we're gonna kind of touch on a little bit but not go into deeply is if I'm finding the average of these numbers versus the average of these numbers, those two averages are gonna be different, right? These guys are between 13 and 18, so the average is gonna be somewhere in the middle. If I put the teacher's age in with this data, it's gonna skew everything up, right? It's assuming 36 is here, so the average is gonna be higher. Let's try that for a second and see what we get. So I'm gonna add all of this plus 36. If I add the 36, that's 11 data points, not just 10. So when I add these together, I get 13 plus 14 plus 14 plus, oh, did I do that right? 13 plus 14 plus 14 plus 15 plus two 16-year-olds plus a 17 plus an 18 plus 36, and I get about 189. So 189 divided by 11 ages gives me about 17.2. 17.2, and that's with the teacher age, right? If I don't include that big number, that teacher age, and I just find these guys, well, it's gonna be this amount minus that 36, right? So 189 minus 36. All of these are gonna add up to 153. There's only 10 of these, so if I'm just adding these up, I get 153 divided by 10 equals about 15.3. So 153 divided by 10 gives me about 15.3, and that's with no teacher, without teacher. Okay, so we can see how the average changes. Adding this in skewed everything up a little bit. Is it true that the average of most of the kids in the class is 17? That's way up here, right? That's not really, because all these numbers down here that's not really the average. This 36 threw everything off. Is it true that the average could be about 15.3? Somewhere in here? Yeah, that's closer to the center here, right? Just a little bit bigger than these guys. So we're gonna use this number. We're gonna ignore the teacher age, and we're gonna look at just student ages. Okay, so that's the mean when you add them all up and divide by how many you have. The median, and you use all these when you're working with statistics, so we do need to know this. The median is when we write them in order smallest to biggest, and we find the middle number, right? So here, I have them smallest to biggest. They're written in order. You don't always have them written in order, so if they're not, you have to put them in order. And then I'm gonna just kind of go in from the outside. So I'm gonna cover up 1 and 1, 2 and 2, 3 and 3, 4 and 4, and now I have 2 here in the middle. They're kind of splitting the middle. So when you have 2 in the middle and not just one number, you're gonna average them together. So we're gonna add them together and divide by 2. 15 and 15 is 30. 30 divided by 2 is 15. So 15 is our median number. 15.3 is our mean. 15 is our median. And then the mode is the number that's repeated the most, right? And so which number out of these up here are repeated the most? 14's repeated twice, 15's repeated 3 times, twice. So it looks like 15. 15's repeated the most. That's our mode. So we can kind of see like our central tendency of all of our data here. Yeah, it's spread out between 13 and 18 years old, but kind of the middle, kind of the middle of the road of all our data is around 15, 15.3, 15, 15. Okay, so that's kind of our statistics here where we're looking at our data. We want to measure central tendency, which means where does the average, the middle of our data tend to be, right? Next thing we want to do is graph these. So we're going to look at a dot plot. Dot plot. A dot plot is like a number line. So you just use all the numbers in your data. So I have 13, 14, 15, 16, 17, 18. 13, 14, 15, 16, 17, 18. And I'm just gonna put a little dot above each number whenever I'm accounting for it in my data. So I've got one 13-year-old, so I'm gonna put 1 dot. I've got 2 14-year-olds, so I'm gonna stack 2 dots. I've got 3 15-year-olds. I'm saying I've got because they're in the class that I'm talking about. I've got 2 16-year-olds. I've got 1 17-year-old and 1 18-year-old. So this is kind of a visual way to represent our data and our central tendency. We can kind of see, and we're going to do a histogram in a second so you get a better visual, but kind of the most amount of data we have is 15-year-olds. That's the most, we have the most 15-year-olds in class, right? And then we've got a few kids that are younger than 15 and a few kids that are older than 15. This is a dot plot, okay? For a histogram, it's kind of similar. It looks like a bar graph. So for a histogram, we're going to use the same data. You're going to have a vertical axis and a horizontal axis. On the vertical axis is the frequency. How many times are each piece of data repeated, right? So we always start with 1. Is it repeated once, 2 times, 3 times, 4 times, 5 times? 1, 2, 3, 4, 5, and I'll put frequency. Okay, and then on the horizontal axis here, we're going to actually use our numbers up here, just like this guy. So 13, 14, 15, 16, 17, oh, I didn't quite make it long enough, 18. 13, 14, 15, 16, 17, that one's supposed to be 18. Okay, so I know that I've got, on my dot plot, I've got one 13-year-old. So here at 13, I'm gonna kind of make a bar, starting at the beginning of my graph to 13, okay? 14-year-olds, how many of those do I have? 2. So for the 14 graph, the bar, I'm gonna go up to 2. For 15-year-olds, I have 3. So I'm gonna go up here to 3. For 16-year-olds, I have 2 of those. 17-year-olds, I have 1, and 18-year-olds, I have 1. So this is a histogram. It has the frequency that numbers are repeated here on the up and down axis, the vertical axis, and what the numbers actually are on the horizontal axis. So then we kind of can look at what our bar graph is doing to figure out if it is an accurate measure of central tendency. The ideal histogram is going to have the biggest, the most repeated number in the center, and then everything to the right, there's about the same amount of data to the right as there is to the left, right? And we're going to talk about that in a second because it can get skewed. We'll look at it in a minute. So that's a histogram. The next one that I wanted to go over with you is a box and whisker plot. Okay, so we're using the exact same data. I'll repeat those numbers again. And we're going to do a box plot. This is also called a 5-number summary. 5-number summary, which you can use for a box plot. Okay, so for this, we're still going to use those same numbers. Let's see, we had 13, 14, 14, 16, 16, 17, 18. 10 numbers here. Okay, so then for this set of numbers, first thing I want to do is find my median, right? All my numbers are in order, so I want to find the middle. I already know it's 15, but I'm just going to do it again. Here, go through here, here, here. It's somewhere in between these two, right? It's right in the middle. So there's my median. I'm going to put an M for median, okay? Then looking at everything to the left of the median. If you have an actual number, we have 10 numbers here, which is an even amount. It's not an odd amount. So the middle is going to be 2 numbers that split the difference. If I had 11 numbers and I counted in like this, the middle would be 1 number and I'd circle it. That would be my median. When the median is not 1 number, the median is here, so I still include this guy to the left of the median. This is not my median, it's to the left of the median. So once I have the median, then I want to go look to the left and I want to find the middle of those numbers. So I go in, 14. Okay, and then to the right, I want to find the middle of all those numbers. Again, this is not the median, so it's included in the right. So I go in, this is the middle. Okay, so now we've split up our data, not by the numbers. We don't care what the numbers are. They could have been in the 30s, the hundreds, we don't care. The amount of data. We had 10 data points, so we kind of split them all up evenly. We've got 2 numbers, this guy, 2 numbers, the median, 2 numbers, this guy, 2 numbers. So 2, 2, 2, 2. Doesn't matter what the numbers are, we just split it up evenly, okay? So this is our first quartile. Since we split it up into 4 sections, 4 quarters, we call this whole guy the first quartile. So 14 represents our first quartile, or Q1. Then we go here to the median, which would be Q2. And we don't ever really call the median Q2, we call it the median. Then the next one is Q3. And then the end over here is Q4, right? We don't really label a number. The first and last numbers, the lowest and the highest, that's part of our range, right? So this is our lower range. The lowest all our data possibly can go is 13. This is our upper range. So when we plot this in a box and whisker plot, we're going to draw a number line, just like before. And we've got 13, 14, 15, 16, 17, 18. And I'll draw little arrows here. 13, 14, 15, 16, 17, 18. Okay, so I'm going to draw boxes around the middle of my data. So first thing I want to do is draw a line at the median. The median is 15. It's the average between these two guys, 15. So I'm going to draw a line here. My Q1 number is 14, so I'm going to draw a line here. And my Q3 number is 16, so I'm going to draw a line here. And I'm going to create boxes. So here's a box, and here's a box. Okay, so these are my two boxes. This is the middle data, my two middle quartiles. That's what I have a box around. And then what we call whiskers are when we plot the lowest point in our range, so 13, and the highest number in our range, which is 18, and we just connect those to our boxes with a single line. Okay, so this is a visual representation of data in a box and whisker plot. This is a 5-number summary because we've got 1, 2, 3, 4, 5 numbers kind of representing our data. Our lower range, Q1, the median, Q3, and our upper range, where I start, quarter of the way through, half the way through, 3/4 of the way through, and where I finish. Okay, so this is called a 5-number summary, where this is a number, Q1, the median, Q3, and the last number. Okay, I hope that makes sense. So we can see here that even though the data is split up evenly into how many pieces of data are in each quartile is kind of spread out differently. So we've got between 2 and 3 numbers here, just between 13 and 14. We've got 2 or 3 numbers here between 14 and 15, 2 or 3 numbers here between 15 and 16, and then we've got 2 or 3 numbers here between 16 and 18. So those are more spread out than the other quartiles were. So we can kind of see that visually. Okay, now the last part here is I want to get into a little bit of standard deviation and mean absolute deviation, right? This is the last part of the video. So we're going to do mean absolute deviation, which is also abbreviated MAD, right? MAD. Okay, so what is this? What are we talking about? Not only do we want to know where the middle of our data is, right? In our classroom ages, it's about a 15-year-old. That's kind of the middle of the road. But we also want to see how much the other numbers deviate from that. How far out are the other numbers spread? Is everyone in the class, 1 or 2 years apart? Or is the youngest kid in class 2 months old and the oldest kid in class 27, right? Like how spread apart are the numbers? So that's when we use mean absolute deviation and standard deviation. And they're two different ways to find similar measures, right? They're both measuring the deviation or how far out the data is spread from the middle. All right, so like it says here, absolute, we're gonna use absolute value. In our data, first thing we want to do when we have this guy is find the mean. And we already did that in the last part here. The mean we said was about 15.3. That's our mean when we just use, remember, we're not counting the teacher age. We're just looking at students. The average was 15.3. So mean is 15.3. For the mean absolute deviation, what we're going to do is take each piece of data, subtract the mean from that data to figure out what's the difference in each piece of data and the mean. How far apart are they, right? So first I've got 13 minus 15, oh, that was a bad 15, 15.3. And I don't really care if they're positive or negative. I'm not concerned about where they are on a number line. I'm just concerned about how far apart the spread is, right? So whether this is positive or negative doesn't matter. I just want to know how far apart it is. So that's why we put absolute value around it. We don't care if it's negative. Just ignore the negative sign. We just want to know how many units different they are. So 13 minus 15.3 is negative 2.3. We don't care about the negative. We just care about the 2.3, right? It's 2.3 units different. So we're gonna add that to, we're gonna do that for every single number. So I'm actually gonna run out of room here, but that's okay. So then I'm gonna use, actually I'm gonna combine some of these. Since I have two 14s, instead of writing them out twice, I'm gonna write a 2 in front and then just write it out one time. 14 minus 5.3. And then the next one I have is 15, and I have 3 of those. 15 minus 5.3. Then I have 2 16s. So 16 minus, I said 5.3, but it's 15.3. I think I'm going to run out of room here. Plus, we're adding together all of these absolute values. So I've done all of these and all these numbers. I'm at 17 and then 18. So I'm going to have the absolute value of 17 minus 15.3 plus the absolute value of 18 minus 15.3. So once we figure out all these absolute values and we add them all together, then I'm just going to divide them by the number of pieces of data I have, which is 10. Okay, so let's just see. We're trying to find the average of how far apart each piece of data is from the middle. So 13 minus 15.3 was negative 2 point something. Oops. 13 minus 15.3 is negative 2.3. And we don't care about the negative, so we're just going to say it's about 2.3 units different. Plus, and then 14 minus 15.3 is negative 1.3. We don't care about the negative. That's why we take absolute value. So it's 1.3. And I actually have two numbers that are 14, so I'm going to do that 1.3 twice. So 2 times 1.3. Okay, so one number has a difference of 2.3, not 5, 2.3. Two numbers have a difference of 1.5, a difference between the number and the average of all the numbers. Plus 3 numbers, 15, I've got 3 of those, have a difference of 15 minus this 0.0. I keep wanting to say 0.7, 0.3. Oh, and we don't care about it being negative, so we just make it positive. That's what absolute value does. 3 numbers have a difference of just 0.3, so they're really close to the middle. 2 numbers have a difference of 0.7. And then we've got this guy, 17 minus 15.3 is 1.7. And 18 minus 15.3 is 2.7. So these are all the kind of variations, right? How far away are they from the middle average? And when we add all those together, we divide by 10. So we're finding the average of not the data now, but of how far apart the data is from the middle. Okay, so then when we add this together, I get 12. And that's being divided by 10. And so that gives me about 1.2. So this number right here is telling me that for each age, for the average difference between each age of a kid in the classroom and the average of all the kids' ages is about 1.2 years, right? So if the middle is 15, the average is about 1.2 years bigger than that or 1.2 years younger than that. That's just kind of our standard deviation, or not standard, our mean absolute deviation, or kind of just what the difference is, the variance. Okay, and then the other thing that we're going to find is very, very similar, standard deviation, traditional standard deviation. It's actually, we're going to do the same thing. We're going to find the difference in each piece of data and the average, each piece of data and the average. But instead of taking the absolute value, we're going to square that difference. And we're still going to divide by 10. And then we're going to go from there. Okay, so last little piece here. This is standard deviation. And this gets a lot more complex as you move into it. We're not getting complex with it. We're just going over the basics. Standard deviation. Okay, so we take our data, 13, 14, 14, 15, 15, 15, 16, 16, 17, 18. All the kids' ages in the class. And we know the average is 15.3. Okay, so instead of doing absolute value, I'm going to start way over here so I have room. I'm going to do parentheses, my first age minus the average, squared, plus, just like absolute value, we're adding them all together. The second age, which is 14, minus the average, squared. And then I've got another one just like that, another 14. So instead of doing it again, I'm just going to put a 2 in front here. I've got 2 of these. Plus, so I got the 13, the 14, the 14. Then I've got a 15 here. So 15 minus the average squared. And I've got 2 more 15. So instead of writing out again, I'm just going to put, there's 3 of them total. So I put a 3 in front here. Plus, then I've got 16. 16 minus the average squared. And I've got another 16. So instead of writing it again, I'm just going to put 2 in front because there's 2 total. And I'm still going to run out of room. Plus 17 minus the average squared. Plus 18 minus the average squared. So that's all supposed to be in one line. It's just a whole lot to write out. And that's all going to be divided by 10. And we're actually going to do something to that number we get at the very end. It's not just going to be divided by 10 and we're done. So stay tuned. All right, so after we subtract each of these and square them, let's go through the first couple here and then I'll pause it and go a little faster. 13 minus 15.3 equals negative 2.3 squared gives me 5.29. So this first value is 5.29 plus, and then I've got this guy, 14 minus 15.3 equals, square it, and it's 1.69, and I've got 2 of them, so I'm going to multiply that times 2, 3.38. Plus this guy, 15 minus 15.3 squared, and then there's 3 of those, so times 3, 0.27, plus, that was this guy, 16 minus 15.3 squared, and there's 2 of those, so 0.98, plus, and then I've got my 17 and my 18, 17 minus 15.3 squared, 2.89, and 18 minus 15.3 squared, 7.29. The further away we get from the middle, the bigger the numbers are going to be. And that's all going to be added together and divided by 10. So when we add it together, we get about 20.1 divided by 10. And then I'm going to divide that, and I get 2.01. And then this is where that extra step is at the end. You know how we squared everything up here? We're trying to find the average. So once we square everything and then add them all together, now we're going to take back that squared and we're going to take the square root. Okay, so when I do that, square root, I get about 1.417 blah, 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 which is about 1.4. 1.4 units. So that's our standard deviation calculation. So again, it's saying if the average of all the kids is about 15.3, then on average, kids can be 1.4 years older than 15.3 or up to 1.4 years younger than 15.3. Now, obviously, we have kids outside of that range. This is just an average. On average, this is how spread apart our numbers are from the center. Right? These ages are all pretty close, which is why this number is pretty small. If you had, I don't know, 10 people that were anywhere between 1-year-old and 99 years old, this number is going to be way bigger because the middle of all those numbers might be 50, and obviously the difference between 50 and 99 is huge, and 1 and 50 is huge, so it's going to deviate from the center a lot more than just 1.4 years, right? So the more spread out your data is, the bigger this number is going to be. This has nothing to do with what the data is, just with how far apart the data is spread. Please let me know if you have any questions on statistics. This was just a basic overview of what you're expected to know for your exam.